Welcome to the next lecture in Fundamental of Electronics. We were discussing the semiconductors, and in this particular lecture we will focus our discussion on doping in a semiconductor. Generally we know that semiconductors are poor conductors. Its conductivity will lie between the insulators and the conductors. So oftenly semiconductors lie in the category of poor conductors. Now the conductivity of any intrinsic, which is the pure semiconducting material, can be drastically increased by controlled addition of certain impurities. So we need to add some impurities in the intrinsic semiconducting material, and in that case its conductivity will increase. This process of adding the impurity is known as doping. So on adding the impurity, it will increase the current carriers, that is the electrons and the holes. So current carriers may be in the form of electrons or holes that we have learned in the previous lecture. So the process by which the impurities are added is known as the principle of doping. When we dope or put impurities in the semiconductor, two different categories of semiconductors are formed. One is known as the Ntype semiconductor and another is Ptype semiconductor, where N indicates negative charge particle will be more and P indicates the positive charge particle will be more. This we will going to discuss in more detail in the particular lecture. So a semiconductor material that has been subjected to the doping process is called extrinsic material. So intrinsic material is the pure form, and when doping process a semiconductor undergoes, then that is known as extrinsic material. Both N-type as well as the P-type material are formed by adding a predetermined number of impurity atoms to a silicon base. So the pure intrinsic semiconductor material, that is silicon, is being added with some impurities with a predetermined quantity that will lead to formation of N-type or P-type materials. Let us first see the N-type semiconductor and then we move to P-type semiconductor. So N-type semiconductor, here the conductivity will be increased by adding the pentavalent impurity to the intrinsic silicon. So when we need to increase the conductivity of an intrinsic silicon material, we add pentavalent impurity atom. Now why the term pentavalent is given to these particular atoms is that the reason is that pentavalent impurity atoms will have 5 valence electrons, and their example are arsenic, phosphorus, bismuth and antimony. These are some of the examples of pentavalent impurity atoms which are having 5 valence electrons. So what happened with these 5 valence electrons in the intrinsic silicon atom? So we can see here that there is one antimony atom which is being surrounded with 4 silicon atoms. So 4 silicon atoms are there which is being surrounded to the antimony atom. So 4 valence electrons of the antimony atom forms a covalent bond with the 4 atoms of the silicon, and 1 extra electron is left over. So there is 1 extra electron which is present when the pentavalent impurity antimony is added to the silicon atom. Now these extra electron will take part in the conduction process as it is not involved in the bonding. So there is no bonding of this 1 extra electron and it is free to have the conduction process. Since the pentavalent atom gives up 1 electron, it is called a donor atom. The reason the name of pentavalent atom are known as donor atom because it is giving an electron to the silicon atom for its conductivity. So conductivity is formed when the silicon atom is given 1 donor atom from the pentavalent. So here we can see that the covalent bonds are being formed by the 4 valence electron and 1 electron is free, which leads to the formation of conduction electrons. Now it is to be noted that in the doping process it creates a conduction electron without leaving a hole. So holes are not generated in the valence band. in the doping process, because the excess number is required to fill the valence band. So one extra electron is formed, but the holes are not formed. So there is no formation of any holes. The reason is that this extra electron is involved in the conduction process, and there will not present any extra hole in the valence band. So in N-type semiconductor, we can say that the majority carriers are the electrons and the minority carriers are the holes. Since electrons are the majority carriers, we have given the name N-type because N here indicates negative. We know that electrons are negative charge particles. So N-type semiconductor will have the majority carriers as electrons and minority carriers as holes. Now let us see the P-type semiconductor. So in the N-type semiconductor, we have added pentavalent. Here we are going to add trivalent impurity atoms. So trivalent impurity atom will increase the number of holes on adding trivalent impurity atoms to the silicon base. So as the name suggests, the trivalent means 3 valence electrons will be present. Example are boron, indium and gallium. These are the example of trivalent impurity atoms which are added to silicon base. So what will have, the number of holes will increase. Now boron will have 3 valence electron and silicon will have 4 valence electrons. So the 4 valence electron of silicon and 3 valence electron of boron. So it means that there is a one hole formation when this trivalent atom is added. So remaining 3 electrons will form the covalent bond, but the 4th electron will result in the formation of one hole, which result in the hole generation in the valence band. Since trivalent atom can take an electron, referred to as acceptor atom. In the previous discussion for N-type, we have seen that pentavalent are donor atom. So trivalent are basically acceptor atom because electron is being taken to form the hole. Now the hole which is created during the doping process is not accompanied by the conduction of free electron. In the previous discussion we have done for N-type that no extra holes are created. Here no extra electrons are created. So only the presence of hole will lead to the conduction process. So P-type conductor will be reverse. Majority carrier will be the holes and minority carriers will be the electrons. So holes are generally thought to be positive charge, electrons are negatively charged and majority carriers are holes. So we have given the name P-type because P indicates to be positive. Okay. So majority carriers are the holes. Now here we can see for N-type semiconductor and P-type semiconductor. In N-type semiconductor, the majority carriers are the electrons and for the minority carriers are the holes. So on having the pentavalent impurity atoms in a silicon base, we can have N-type semiconductor. In the P-type semiconductor, the majority carriers are the holes and the minority carriers are the electrons and trivalent impurity atoms are added to it. Then we can have N-type and P-type extrinsic semiconducting material. We have discussed that semiconductors will have the conductivity lying between insulators and the conductor, and there is a definite gap between the conduction band and the valence band. This gap, which is known as the gap energy, which is more than 5 electron volt for the insulator, but for the semiconducting material like germanium, silicon and gallium arsenide, it is 0.67 electron volt, 1.1 electron volt and 1.43 electron volt respectively. So this gap will not have, this is known as energy gap between the valence band and the conduction band. There no charge particle present, and when some external heat energy is given, the electrons jump from the valence band to the conduction band for the conduction process. In the conductor, we have seen that conduction band and valence band overlap each other. When we talk about electron volt, what is the meaning of that is the energy is given as charge into voltage, and charge of one electron is 1.6 into 10 to the power minus 19 coulomb, and when we give 1 volt voltage, then we get 1.6 into 10 to the power minus 19, the unit is in joule. So 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. So this is the energy of 1 electron volt. And this is the semiconductor material in the intrinsic state when the pure semiconducting material is there. Now what happened when we dope the semiconductor? Like for example, if you have the donor energy, then in that case the gap between the conduction band and the valence band, which was here more in case of the intrinsic semiconductor material, that will decrease in case of the extrinsic semiconductor material when some impurities are added. So in this particular lecture, we have focused our discussion on the donor and acceptor type of impurities, that is the N-type and P-type semiconductor material. And now this N and P-type semiconductor material will be combined to make the diodes. That will be the focus of discussion in the next lecture. Thank you for now.